Thermal properties phonon. Phonon heat capacity. Heat capacity is a material's property which converts absorbed energy into a unit increase in temperature. Knowing the heat capacity of a material can help you answer questions like if I shine a laser of known power and frequency onto a given crystalline solid and I know the optical absorptivity of that material for that frequency of light, how much will the region exposed to the laser beam heat up? If I put a copper pin on a hot plate powered by known voltage and current, what is the maximum temperature it can reach in 5 minutes? In this derivation, we will consider the heat capacity at constant volume, defined as Cv is equal to partial U over partial T power V, where U is the internal energy and T is the temperature. There is also heat capacity at constant pressure, which is given by the temperature derivative of the enthalpy. H is equal to U plus PV. The two types of heat capacity are related to each other by the thermodynamic relation. Cp minus Cv is equal to 9 alpha square BVT, where alpha is the coefficient of linear thermal expansion, V is the volume and B is the bulk modulus. The total energy U of phonons at a given temperature is given by sigma k sigma p n k p h cut omega kp, where the sum over k is summing up all available momentum state. E.g., momentum is quantized, so we consider each discrete value and look at the frequency omega. We consider each discrete value and look at the frequency omega at that value according to the dispersion relation. The sum over P is summing up all polarizations. This is another way of saying you are summing overall phonons branches. Longitudinal acoustic, transverse acoustics, longitudinal optical and transverse optical. For a material which occupies d dimensions and has p atoms per basis, there will be a total of dp polarizations, with d of them being acoustic and d into p minus 1 f of them being optical. Permissible omega kp is called a normal mode. Nkp is the number of phonons with momentum k and polarization p which are expected to be occupied at a given temperature. This is the term which allows us to take a temperature derivative to derive heat capacity because the other terms are not temperature dependent. Some general intuitions about this term. At a given temperature, lower frequency modes are more likely to be occupied unless the temperature is really high. Has a maximum phonon frequency, so at sufficiently high temperature, all modes will be equally occupied. Monatomic solid made up of three-dimensional oscillator. Its total internal energy per mole is given by U is equal to 3 nkBT, where Kb is Boltzmann constant, but R is equal to nkB is a universal gas constant and N is Avogadro number. So U is equal to 3RT. Hence, by definition, Cv is equal to du over dt. Cv is equal to d over dt 3RT. Cv is equal to 3R d over dt t. Cv is equal to 3R. This equation indicates that Cv is independent of temperature and referred as Dulong and Petit law. This law is found to be obeyed by heavy elements atomic weight greater than 40 at high temperature. But at low temperature, Cv is found to decrease with temperature and finally reach to 0 at 0 Kelvin. This discrepancy was solved by Einstein on the basis of quantum ideas. The schematic picture which shows the graph between temperature and specific heat obeying Dulong and Petit law.